So good morning, students, and welcome to today's session. So I think all students are more or less present now, so we will start the session. So as you must have seen in the timetable, today we start with one of the sections of physics called calculus. And the name calculus might be unfamiliar to some of you, but do not worry, I will explain everything about calculus and what it means, etc. So it's a very interesting branch of physics, and also it is an idea in physics and mathematics which is very, very important in all future aspects of physics that we are going to do. So in other words, simple mathematical tools like addition, subtraction, division, etc. were what we required in physics up to 9th, 10th level. But when we come to physics at the undergraduate level, or even at the intermediate level of 11th and 12th, we need some additional mathematical tools to be able to describe physics and understand physics, and to be able to work out the many equations that we'll be deriving in physics. And calculus is one of those tools. Hence, what we are going to discuss in the coming few weeks in this section of calculus is going to look more like mathematics than physics, but basically it is a branch of uh, applied mathematics in physics, you can say. So calculus is very much about the basics of physics. Okay. So anyhow, let me start by introducing myself. I think this is my first lecture with this batch yellow, or many of you might have attended an introduction lecture before with me. So my name is Bhattacharya. I'll be teaching you physics, certain parts of physics in the next 2 years. And welcome to all of you to the beginning of your journey towards JEE and towards your goal of getting into the IITs, etc. Okay. So session 1 of basic calculus. Okay. So before we get into the physics, few general things I want to tell you. First of all of you must have received the modules. Module 1, either you'll be having a physical copy of it, or at least you have the PDF of it. You can collect the physical copies once we are through this difficult time of the second phase of Corona. So once we are through with that, we will be able to call you to the centers to give you the booklets, and also for small doubt sessions, etc. And eventually we expect things will clear out, vaccinations will be complete, and we'll be able to go back to our regular plan of physical lectures. So in the meantime, please refer to the PDF module 1 of physics in case you don't have the physical copy. So in module 1, basic calculus is the second part of it. The first part is vectors. The session that we were supposed to have earlier today unfortunately got cancelled because at Hemant sir's end there was some internet connectivity issue. So don't worry, that will start in the next lecture. I mean, the next time you have a session with him. So vectors and calculus are two parts of physics that we will be starting with initially, because we need to understand these two aspects before we get into anything else in physics, like whether we are going to study Newton's laws of motion, or we're going to study about work by energy, or about kinematics, that is the equations of motion itself. We need to have a background in these two things: vectors, which deals with physical quantities called vectors, which have both magnitude and direction, and the other thing is calculus, which deals with things like rate of change, functions, etc. Okay, so let's get more into that. So to understand the the crux of calculus, where it all came from, you have to actually go far back in time in physics, to, let's say, sometime around the mid 1600s, round about the time of 1660, if I'm not mistaken, when Newton made the astonishing discovery of gravity. And as the legend goes that he was sitting in his garden and he just observed an apple falling, and by simple deduction on the fact that as the apple was falling, its speed tended to increase, he realized that there is some kind of a force acting on it. Otherwise it would have tended to fall in a uniform motion with constant speed. So the fact that as an object falls near the surface of the earth, as it is in free fall, it gains momentum, or it gains speed. That means there must be some kind of a force attracting it towards the surface of the earth, and that force is the gravitational force. So that led to, so of course, as I said, as the legend goes that he had a eureka moment when he saw the apple falling, but obviously behind that eureka moment there were years and years of deduction and analysis. So there's a lot that led to that single moment of moment of that light bulb moment, you can say, when he realized that there is there is such a thing as gravity and coined the name, etc. But there's a lot of analysis and deduction that that had gone into that process, which led to that moment. So the science of calculus, or the mathematics of calculus, you can say, actually almost dates back to that similar kind of period. Newton was one of the original people who developed the mathematics of calculus. So calculus is attributed to Newton and another scientist called Leibniz, a French guy. So Newton and Leibniz actually worked together through correspondence for a certain part of the development of calculus, and of course, true to human nature, later they had their own differences. So there was some controversy also between them about who had discovered which theorem in calculus and this and that. So there was some infighting also. But yes, widely speaking, calculus is attributed to Newton and Leibniz as far as the early discovery is concerned. So let's instead of worrying about immediately what is calculus, what are the different symbols, what are the definitions, etc., let's just explore one simple concept in physics related to motion, and through that we will understand how calculus itself came to be. Like what was the problem that we were trying to solve in physics that led to the whole development of calculus as a branch of mathematics. Okay, so that problem, let's say, is the problem of motion. Okay, so if we look at motion, and in motion we are talking about things like distance versus time, okay, and the concept of speed. Okay. So and to simplify things further, let's take an even more easy example. Let's talk about motion along a straight line. Like, let's say we have a situation where we have, let's say, the x-axis and an object is moving along the x-axis. Okay. So at a particular instant of time, the object is located here. At a different instant of time, let's say t prime, the object is located here at a coordinate x prime, or is at a coordinate x, etc. So can anybody tell me how we define the quantity speed? How do we define the quantity speed? You can unmute yourself and just answer the question. You can raise your hand and unmute yourself, or you can even send me the answer in the text message. I'll just send you an example text message to show you. So what is meant by speed? Okay. So anybody wants to answer the question directly, you can unmute yourself, or you can send a reply text message to me, like I've sent you all a message right now. Speed is the distance moved by the body in unit time. That's the answer by Archit. Very correct, very precise. Distance traveled in unit time. Distance traveled by a body in a time interval. That is the answer given by Shubham, Yash, Siddharth. Okay.
Sir, I'm not being able to send messages to you.
You're not being able to send messages?
Yeah, it's telling that Bhattacharya is not in the meeting.
Okay. I don't know. I'm getting messages from others. Maybe you need to re-log in, but don't worry. You can just answer like this one.
Yes, sir.
Okay.
Speed is a distance covered by a body in a given time period.
Speed is the distance traveled by the body in a given interval of time. Yes, that's correct. Okay. I'm just checking if there's something wrong with your settings. Nirudh. Yeah, you should be able to send messages. Okay, maybe just some software error at the moment. Krish, correct. Distance upon time. Okay. Now let's ask a more precise question. Okay. Now, supposing I ask that, okay, supposing the straight line motion is happening such that, at t equal to 0, when the motion started, the x coordinate of the particle was, let's say, 0. It started from the origin. Okay. Then I'm observing that, okay, at some time, let's say 1 second, the x coordinate is becoming 5 meters, let's say. And then further at some new time of, let's say, 3 seconds, okay, the x coordinate is becoming x prime, which is, let's say, 8 meters or something like this. Okay. So as the body is moving, this is what is happening. Now, when I talk about, yes, so all of you have, suggested that speed is some kind of relationship between distance and time, where we can say it is the distance with respect to time. Okay. Or more precisely, we can say that the speed is equal to the rate of distance covered with respect to time. Okay. And if you're talking about motion along a straight line, the distance covered is a very simple thing. The distance covered S will be nothing but the final x coordinate minus the initial x coordinate, or we can say it is equal to x2 minus x1. Okay. Now I'm assuming that the particle is not turning back, okay, or the body is not turning back. Okay. So I'm talking about distance in that situation where it's moving along a straight line, okay, along one direction. It's not turning by 180 degrees. So then we can say that the distance is equal to the change in x coordinate, or x2 minus x1, or delta x, or whatever we can say like that. So it is the rate of distance covered with respect to time. So many of you have also described this as the distance covered per unit time. Okay. But now I can be more specific here. So referring to the diagram above over here, what if I ask you, what is the speed, or what if I ask you, what is the distance from 0 to 1 second? Okay. Then again, what is the distance from, let's say, 1 to 3 seconds? Okay. And then again, what is the distance from 0 to 3 seconds? Can you give me the answer of these three parts separately? So imagine this is what is happening. Okay. It is moving along one direction. It's not reversing back or anything. So an object moving along a straight line along one particular direction. If I have these three pieces of information, that at t equal to 0, its coordinate was 0. At t equal to 1 second, its coordinate became 5 meters. And at t equal to 3 seconds, its coordinate became 8 meters. So what can we say about these three? Okay. Yes, very good, Archit. That's correct. Okay. Correct. So all of you are getting the answers. So as you can see, this should be nothing but x minus x naught according to how I've written it. Okay. So it should be 5 meters. Okay. This should be x prime minus x, because 1 to 3 seconds. So this should be 8 minus 5, or 3 meters. And therefore, obviously, this should be the sum of these two, because it's not changing direction in between. So it should be 8 meters. So what we can see, in the first 1 second, it is covering a distance of 5 meters. In the next 2 seconds, it's covering a distance of 3 meters. And in the next, or in the 3 seconds from 0 to 3 seconds, in that total time interval, it's covering a distance of 8 meters. Now coming back to speed. Okay. What can I talk about speed over here? What information can I get about speed from the above diagram?
The speed is non-uniform or variable.
Yes, very good. That's one very precise observation. Sorry, I didn't catch who gave that answer. Can you just raise your hand? Yeah, Anirudh, very good. That's correct. Okay. I'm receiving some answers on the text also. Yes, very good. Rhythm, that's correct. That the speed is variable. Okay. Krish, yes, we can observe something about instantaneous speed. We can observe something about non-instantaneous speed also. So now one of the things that you can observe now over here from this information is that speed is variable. Now, Anirudh, can you explain how we came to this conclusion? How did you come to this conclusion that speed is variable?
Yes, sir, because the body covers unequal distances in equal intervals of time.
But do I have equal intervals of time from the information given? Because देखो मेरे पास जो पहला interval है ना, this interval is how much? This is 1 second interval, correct?
So
Okay.
if we take it as 1 second, it is unequal.
This is 2 second interval, right? This is 3 second interval. Okay.
So if we take it as 1 second and if we try to divide it, it becomes unequal.
Yeah. So in other words, let me give you a hint. Have you heard the term average speed? Any of you have heard the term average speed?
Yes, sir.
Right. So what is average speed?
Total distance divided by total time taken.
Total distance divided by total time, right? Anybody else wants to answer anything about average speed? Okay, so I think we all agree with the fact that average speed kya hota hai? Average speed, first of all, we define for an interval of time. Now, there's no point in saying what was your average speed at 12 o'clock. There is a point in saying what was your average speed from 12 o'clock to 12:30, or what was your average speed from 11 to 1. that makes sense. But if I ask you what was your average speed precisely at 11 o'clock, the question only doesn't make sense, right? Because average speed has to be defined for an interval. So if I define average speed as the total distance traveled in an interval of time divided by the time, then I can observe that for each of these intervals, I have a different value of average speed now. Because in this 1 second interval, it traveled how much? 5 meters. So the average speed for this time, that is 0 to 1 second for this interval, the average speed is precisely how much? It is 5 meters per second. But then if I observe from 1 to 3 seconds, what is the average speed? It is reduced to 3 by 2, in fact. It's reduced to 1.5 meters per second. So the fact that the average speed itself is changing, that is telling me that the speed is variable. So how I'm getting this information? So to get this information, I have to apply the definition of something which may not be so familiar to all of us. I have to apply the definition of the concept called average speed. Okay. And of course, there is also the concept of instantaneous speed, which Krish you have made. And we'll talk about instantaneous speed in just a moment. But the easier definition over here is average speed. According to what information I have, the easier definition is average speed. So average speed is defined as what? It is defined as total distance, okay, but in a certain time interval. And that time interval has to be very precise. It has to be defined as delta t equal to some particular moment of time t2 minus some initial moment of time t1. Okay. So that total distance during that time interval divided by the time interval, which is basically delta t, which is t2 minus t1. Okay. So that means average speed is defined for a specific interval of time. We can only define the average speed when we are sure what this interval of time is. What is the value of t2 and what is the value of t1? Okay, so it becomes t2 minus t1. So if we apply this definition now to the above situation, if we apply this definition to the above situation, then we can see that for each of these intervals of time, we can define how much the average speed is, because we know the distance traveled and we know the time interval. So for example, in the above situation, in the A part, delta t from 0 to 1 second. Okay, my average speed from 0 to 1 second will become how much? It will become 5 meters divided by 1 second. So it will in fact be 5 meters per second. But for the second interval, from 1 to 3 seconds, I can see my delta t is 3 minus 1 or 2 seconds, whereas the distance is equal to 3 meters. So in fact, the average speed from 1 to 3 seconds will just become 1.5 or 3 by 2 meters per second. Okay. So for example, these two values I hope are clear to all of you. If there's any doubt, please let me know immediately. Okay. We are not in any kind of hurry. Okay. So if there's any doubt at any point of time in class, you can always ask me, whether you send me a text message or you just raise your hand or reply by by unmuting yourself. Just treat it like a normal class. There's no difference between a regular lecture and this. The only difference is that we're not in the same room. All right. Similarly, C part, can you tell me how much the average speed is from 0 to 3 seconds? If I take this interval, how much is the average speed? Yes, how much should it be for the third part?
8 by 3.
8 by 3, that's very correct. Okay. So that's again different. You can see the average speed in 0 to 3 seconds is 8 by 3. That will become 2.67 and approximately, or 8 by 3 meters per second. So this is now giving me a conclusive proof of what I said earlier, that it has variable speed. Okay, now like Krish has actually said, variable speed actually refers more to instantaneous speed, and I'm coming to that point, that the instantaneous speed will definitely not be same. But I can also get evidence that okay, the speed is changing, because though I don't have information about instantaneous speed yet, I have information that the average speed is changing for different intervals of time. So what this is showing, that average speed is different or varies for different intervals. So that itself is a proof or an indication of the fact that the speed is variable. So this statement on its own implies that it is having a variable speed. Okay. Now, before we move on to the concept of instantaneous speed, now in this same question with the information that I have given above, okay, if I asked you that what is the average speed from 2 to 3 seconds, what would your reply be? What is the average speed from 2 to 3 seconds? Anybody, what answer should we give?
We don't know the average speed between 1 and 2 seconds, so maybe it's not
Yes,
possible.
very good. So there is no way we can calculate this. Okay, from the information given, this cannot be determined. It's correct. Why this cannot be determined? Because there is no information telling me about the distance traveled. Either neither I know between 1 and 2 seconds what is happening. T equal to 2 seconds पे, what is the value of x? I don't know. Na? So neither I know what's happening between 1 and 2, nor I know what's happening between 2 and 3. So there's no way I can calculate this average speed between 2 and 3. So there is lack of information. There's insufficient data. So our answer should be that there is insufficient information, okay, or insufficient data to calculate this. That's simple. Right? This is clear. So like I will be sending you, PDF notes of my class notes, this whiteboard notes that you are seeing. So you need not make yeah, this is one of the points I forgot to make in the beginning, that as far as your general method of lectures and notes and all this is concerned, for each of the different tracks that you're studying here, you should have a separate notebook. So like for physics, you are studying 2 tracks right now, vectors and calculus. So you should have one separate notebook for vectors and one separate notebook for basic calculus. And in my case, I will be giving you the whiteboard PDF notes of my lectures. So you don't have to make very detailed notes during the class. Okay, during the class, you can put more effort into concentrating on, understanding the concepts. And, when we are doing numerical problems like this, and I give you a bit of time to work out something, then you can do that numerical part. But yes, it would help if you jot down the important points, because writing just makes things clearer in our head compared to just seeing and, just seeing and hearing. So you don't need to make absolute fair notes while the class is going on. You can just make some kind of rough notes. And later, if you want, you can, like, referring to the PDF notes that I'm going to send you, you can make your fair notes. Okay. Yeah, so with that point, if you just want to jot down any particular points of this or make sure you understand these calculations, I'll just give you a minute for that, then we'll go on to the next concept. Okay, so you'll also notice that apart from the fact that speed is variable, we can also see that from this we can find average speed for time intervals which we have labeled as A, B, and C. Okay. But what we can also see here is that We don't have information about anything else as far as speed is concerned. So no other information for speed is available. From what I have given in the question above, these are the only things that we can say about speed. That what is the average speed in the interval A, what is the average speed in B, and what is C. And because they happen to be different, so from that we can conclude that yes, the first point, that the speed is variable. But if I ask any other information about speed, like what is average speed for some other interval of time, like 1 to 2 seconds, or 2 to 3 seconds, or 0 to 2 seconds, I have no information. Okay. And I have not even come to the point of instantaneous speed yet. We are coming to that point next. Okay. So assuming that all this is clear, okay, please let me know if you have any doubts. Now let us come to a much more interesting concept, the concept of instantaneous speed. What do we mean by this term? Okay. How do we describe the term instantaneous speed? Yes, anyone wants to elaborate on what is instantaneous speed?
Speed changes every second.
Speed changes every second. Yeah, you can say that in a sense. Okay. But is it just that it changes every second, or can the second be divided into smaller interval also?
The speed of the body at any instant of time.
Yes, yes. Yes, your answer is very precise, very good. Okay. Freya, your answer is also correct. Okay. Rhythm, your answer is correct. Okay. So as the name suggests, okay, distance, Bhavika is saying that it's the distance traveled by a body at a particular time t, so that the speed is at that instant. Okay. Let's understand this. Yeah. So what we mean, so as far as nomenclature is concerned, as far as the name is concerned, what does the term instantaneous mean? The term instantaneous means at an instant. Okay. Precisely, but that's a simple definition of the word instantaneous. What does instantaneous mean? It means at a particular instant of time. Okay. So for example, if I ask what is my age at this instant, if I ask what is the age at this instant, so I know that right now it is, whatever, 28th of April 2021, and let's say precisely the time is 11:29 a.m. Okay, whereas if I know my date of birth, okay, suppose my date of birth is some day, some month, and some year, and a particular time, let's say it's 12 p.m. So precisely at this moment, what is my age? So if I know the time up to minutes, then I'll be able to tell what my age is up to a certain minute. Okay, so I'll be able to tell that it's 28 minus X days, okay, plus April minus Y whatever months, okay, plus 2021 minus Z whatever years. Okay, and like this I'll be able to tell so many hours and so many minutes. So I'll be able to tell my instantaneous age up to a certain amount of minutes if I know the time in minutes. Okay, so I'll be able to say that it is N1 years, N2 months, okay, N3 days, N4 hours, and N5 minutes. So the precision of my answer is up to minutes. But suppose I observe the time in seconds. Okay, suppose I observe the time right now that it's 28th April 2021 and 11 hours 30 minutes, and suppose just now when I was starting the question it was 42 seconds. Okay, and similarly I know that my date of birth was, let us say, 9th of February, okay, 1981. Okay, and suppose it was some 10 a.m. and 2 seconds. So now you can see that my instantaneous age is becoming how much? It is becoming a certain number of days, years, and all that, but precise up to seconds. Okay, all those things, and 40 seconds, because this is 42 and this is 2. So now my accuracy of the instantaneous age has gone up to a second. Similarly, if I had expressed it in milliseconds, then the accuracy would be that much more. So it becomes a matter of measurement. Okay, so whenever we express something instantaneously, the instantaneous value of any parameter it's the value of that parameter at an instant, and the accuracy of this measurement, okay, the accuracy depends on the measurement, how precise we are doing it, or precision. For example, if X is the population of India, okay, instantaneous population of India, now the accuracy depends on whether I'm doing it on an hourly basis or I'm doing it on a daily basis, that every day I count the population of India, I have some census which counts it, or I'm doing it on a minutely basis, so I know what is how the population is changing according to the number of births and the number of deaths every minute. So my measurement of the instantaneous value of this parameter X, which is population, depends on how I'm measuring the population, how often I'm measuring the population. The accuracy depends on that. Okay, so that is the point I was trying to make. Now coming back to instantaneous speed, coming back to the point of instantaneous speed, so we generally denote with a symbol V instead of V average. So this is nothing but speed at an instant. So let's try to understand what we mean by speed at an instant. Okay, now let's think practically. Okay, like let's do an experiment which would be rather easy to do. You're just traveling in your vehicle, right? You're traveling in your vehicle with presumably one of your parents or somebody who has a license to drive. So how would you measure instantaneous speed? How would you know the instantaneous speed? Like, let's say you were traveling between 11 and 12, and I asked you later that what was your instantaneous speed at 11 hours, 30 minutes, and 52 seconds. So what would you require to do that measurement?
So the time at which we started and the amount of distance we covered at that point.
No, beta, that will give me average speed, no? Like, for example, if I started at 11 o'clock, okay, and I asked you what is the average speed from 11 o'clock to, or what is the average speed at 11:30 and 52 seconds, then you would say that, okay, from 11 o'clock to 11:30 and 52 seconds, I'll first measure how much distance I covered and divide the distance by the time. But instantaneous speed at 11:30 and 52 seconds, how would you measure that? Is there some device in your car which measures that?
Speedometer.
Speedometer. Yes, Krish, instantaneous time intervals and distance. So which is the device that measures that? It's the speedometer. Okay. Now, if you notice, generally speaking, unless you are, unless you're in an extraordinary situation where you're driving on a straight road without accelerating or braking at all, what does your speedometer's, needle or indicator show? That it's changing from instant to instant, right? That is what you mean, Krish, by saying that instantaneous speed changes every instant. So if it is changing from every instant to every instant, like right now I'm looking at it, it's pointing at a certain value, 60 kilometers per hour. But even a millisecond later, it might change, or at least a second later, it will change, because it's very unlikely that I'll keep moving at the same speed. So how is it actually measuring that? And what is the speedometer measuring? Any idea about that? Like, this is a general question, like more like a general knowledge question than a physics question. How does the speedometer actually measure the instantaneous speed? What would you guess it measures? Okay. Ajay, is there any relationship between the rate at which the wheels are rotating and the instantaneous speed? There should be some kind of relationship, right? Yes, there is. So if the speedometer's machinery is directly connected to the transmission of the engine, it can measure what is called RPM. Krish, your answer is correct. RPM is rounds per minute or rotations per minute or the number of turns per minute that your engine is transmitting through the axle system onto the wheels. So yes, very correct. Archit, that's good. The amount of rotation actually relates to the speed. Okay, and this is again related to a very simple concept in physics, which was discovered, long before Newton's laws and all by the Greeks, that if you have any round object like a cylinder or a sphere or something, okay, which is rolling on the ground, the wheels of a vehicle typically are rolling on the ground, unless of course the vehicle is skidding. Okay, unless the vehicle's wheels are skidding, the wheels are rolling on the ground. That means the point of contact is not slipping. So if this point is over here at a particular instant of time, okay, let's say on a cylinder or a wheel or whatever, you just made a small mark with a with paint or something like this. So at a later instant of time when the wheel has reached here, okay, now because what's happening, the wheel is rotating and at the same time also moving like this. So the center of the wheel has moved from here to here, but the point A might have moved somewhere here because it's also rotating. Okay, so you can see that this diameter AB, it has rotated like this. The point A has rotated from here to somewhere here. But at the same time, while the point A has rotated, the wheel has also moved forward. Okay, so like that, by the time the wheel makes a complete rotation, okay, that is the point A is back to contact with the ground. Okay, so this is what we'll call as one cyclical time. If this was t equal to 0 and this is capital T, we can say that capital T is the time taken for one cycle, okay, or one rotation of the wheel. So in one rotation of the wheel, how much is this distance going to be? Can you tell me how much this distance will be?
Circumference of the circle.
Very nice. It's going to be equal to the circumference. Okay. Is this just an intuitive answer or can you actually give some logic behind it? Why it should be circumference?
Because it is rotating as it moves forward along its circumference.
It's rotating, and also, I'll just give you one hint to what I'm saying. That remember, the wheel is not skidding. It's not slipping on the ground. No? Okay. Now think of a simple experiment. Like suppose I sprayed some paint onto the wheel, a paint that can stain the ground. So what happens as the wheel rotates by one full cycle and rolls over? What will happen? Every point where the paint is sprayed is coming into the contact with the ground somewhere or the other, right? So what will be the length of the paint stain? It will be the length of the circumference in one cycle, right? So that is a simple proof that in one rotation, this is what the Greeks had discovered, that in one rotation, if an object is rolling, it is covering a distance of 2 pi r. So what our speedometer does is, it is able to measure the rate at which the engine is transmitting angular speed, or the rate at which the engine's axle is rotating in rounds per minute. So from that, it is able to measure what is the time taken per cycle. Okay, so don't worry about exactly how that happens, but I'm just giving you an idea. So once the speedometer is able to precisely tell what is the rate at which the wheels are rotating, it is able to precisely do this calculation. It can do S upon T, where T is one cycle and S is equal to 2 pi r, the distance traveled by the axle of the wheel in one cycle. Okay, so that is how it is giving you the measurement of instantaneous speed. So when you look at your speedometer at a particular instant and it shows, let's say 40 kilometers per hour, it means that one circumference divided by the time taken for that circumference or that distance to be traveled is equal to 40 kilometers per hour. So if you were moving at constant speed without accelerating or decelerating, then in the next 1 hour you would cover exactly 40 kilometers. But there's no guarantee you're going to be doing that, right? Because you might be braking in the next instant, you might be accelerating in the next instant. But at that instant, the rate at which distance is covered with respect to time, that is equal to 40 kilometers per hour or whatever value it is. So in other words, what is instantaneous speed? Instantaneous speed is also distance upon time, but the difference is it is distance upon time for a very, very small interval of time. And some of you have given this answer very precisely. I was happy to understand that. Okay, so it is like average speed. It has a definition that is the total distance okay, in a time interval. Okay, so you can write it is equal to S from time t1 to t2 divided by the time interval t2 minus t1. Okay, that is our average speed, and we saw how we put this in practice in that particular question. But what is our instantaneous speed? Our instantaneous speed is the distance divided by the time, but for the specific condition where delta t should be a very small, an extremely small interval of time. And in fact, the smaller the interval of time, the more accurate our measurement is. Okay, the smaller the value of delta t, okay, the more accurate is the measurement of instantaneous speed. Okay, now you might have, for example, heard of the term speed gun. Have you heard of the term speed gun? Can you give me an example where it is used?
So it is used by the police to measure the speed of a car.
Yes, correct. It is used by traffic police. Example, okay. Traffic police use speed guns to monitor vehicular speeds and fine people and all that. No? Anywhere else you have heard the term speed gun being used? Any sports fans here?
In cricket, to measure the speed of the ball.
Yes, very good. You know, in cricket or any kind of sports. Okay, for example, tennis, the service speed, cricket, bowling speed, etc. So what does a speed gun actually do? Now the speed gun is more interesting. Usually modern day speed guns work on infrared. So for example, you know that, let's say, a bowler is going to run like this, and I'm going to struggle to draw this, but let's say one of his arms is like this and the other arm is like this, and he's going to pitch the ball from here. So the ball is going to go in not a straight line motion, it will go in what is called a projectile motion. Okay. But what a speed gun will have is it will have an infrared sensor somewhere over here. Okay. And again, it will have an infrared sensor at a later distance. So there are two infrared sensors. And sensor 2, okay. So the first one will give you a signal, let's say at time t1 when the ball crosses it. The second one will give you a signal again at time t2 when the ball crosses that one again. Okay, and this distance L between them is known. So it will calculate the instantaneous speed as L divided by t2 minus t1. Okay, so how that typically works, that sensor thing is, it's like a three-dimensional thing. Like if this is the cricket pitch, for example, so there will be, like, you know, a set of sensor lights set up. I mean, of course, this will not be right at the pitch. It will be somewhere, you know, further down like this. And there will be a receiver for that light like this. So it's sending light rays across the pitch like this, sending a whole wall of light like this. And as the ball goes past that, it obstructs at a particular point. So when it obstructs, it gives a click. It measures that value of time. Okay. And then somewhere further down the pitch, there is a second set of sensors, an infrared detectors on this side and source on this side. This is again sending a second set of beams like this. So between this post and this post, as the ball crosses, it's able to measure the time difference. Okay. Now suppose I have one setup that measures this for a time difference of 1 millisecond, and a second setup that measures this for a time difference of 0.2 milliseconds. Then which one will be more accurate? The one which measures for 0.1 milliseconds, right? The lower the time interval, the more accurate is our measurement. Okay, just like I said, for any instantaneous parameter, like if I'm telling you my instantaneous age, so if I'm measuring time up to a millisecond, then I'm giving you a very, very accurate value of my instantaneous age up to the millisecond. If I'm measuring time using a normal wristwatch up to only a second, then I'm giving you a less accurate value of my instantaneous speed up to second. If I'm going by the calendar, then it's only up to a day. So I'm giving you a further less accurate value of the instantaneous age, which is accurate up to a day. So similarly, when we talk about instantaneous speed, okay, the lesser the interval of time, the more accurate it becomes. So in instantaneous speed, B is equal to delta S by delta T, where delta T should be an extremely small interval of time. So for example, if I'm asking you to measure the instantaneous speed, okay, at t equal to 2 seconds, let's say. Okay, because instantaneous speed basically means that it means speed at an instant. And practically what was happening is that we are back to that first situation, that we had an object that is moving along the x-axis. So suppose this object was here at t equal to 0. Then it was somewhere here at t equal to 2 seconds. Then it was somewhere here at t equal to 3 seconds. Okay. That's not going to help me so much if I know the value of this and I know the value of this. It's not going to help me so much. What's going to help me more is if I know the value of x at a time which is slightly greater than t. Okay. Where delta t is a very small interval of time. So if I know this distance from here to here, then that's going to be of immense help when I'm trying to calculate. Okay. So over here, this small distance divided by this small time, this will be the instantaneous speed. Okay. This will be the instantaneous speed. At t equal to 2 seconds. So for example, that delta t might be 10 milliseconds. Okay, so I'm calculating delta S by delta t for whatever distance traveled from 2 to 2.01 seconds. This is the distance from t equal to 2 to 2.01 seconds. Okay, because 1 millisecond, 10 milliseconds is the same thing as 0.01 seconds. Okay, divided by delta t, which will be 0.01 seconds. So that is how I'll be calculating if I take delta t equal to this much. But if, let's say, a competitor of mine takes delta t equal to 5 milliseconds, then what he is doing is he is measuring delta S as the distance from t equal to 2 seconds to t equal to 2.005 seconds. Okay. So because he is taking the interval of delta t equal to 0.005 seconds. So now what he is measuring as the instantaneous speed will be this distance, okay, from 2 to 2.005 seconds divided by 0.005 seconds. That's 5 milliseconds. So this will be how he is calculating the value of instantaneous speed at t equal to 2 seconds. So you can see that his calculation is going to be more accurate than my calculation, because I am calculating for a delta t of 0.01 seconds. He's calculating, so you can see that this one is more accurate. This one is less accurate, comparatively less accurate. Both are reasonably accurate because I'm taking quite a small interval of time. But in comparison, this one is now more accurate than this. Okay, so this is a sort of practical meaning of the term instantaneous speed. Okay, practical meaning of the term instantaneous speed is what? It is again distance upon time only, but for a very, very short interval of time. The shorter the interval of time we are able to do that measurement for, we can say the more the accuracy of our measurement. Okay, is this point clear to all of you people? Okay, so I'm just going to give you a couple of minutes to go through this section that we have discussed. Okay, if you want to jot down any points or anything. So in this part, we have actually not talked about speed at all. This is like the general meaning of the term instantaneous. What we mean by instantaneous. Same. In this case, we are discussing about instantaneous value of any parameter. And the example we have taken is population. The example we have taken over here was instantaneous age.
So can you please scroll up?
Yeah, sure. Okay, done with this?
Yes, sir.
Okay, now let's come to an interesting situation that Newton would have been thinking when he came across that falling apple and that concept of gravity, and from where he would have started thinking along the lines that led to the development of calculus. Okay. So he had already established his Newton's laws of motion by then. So the first law, Newton's first law, as you know, it says that a body will continue in uniform motion, okay, until and unless acted upon by an external force. So by uniform motion here we can say uniform or constant velocity, which also means that the speed will be constant because velocity is both magnitude and direction. Okay, so magnitude of velocity is speed, and okay. So now for this, if we visualize practically, if we want to visualize a situation where this is happening, so we come back to the earlier example I was telling you about, that you have a perfectly smooth surface. So it's perfectly frictionless. Okay. So you know that practically this is not 100% possible, but you can come to a very close to a perfectly frictionless surface, especially if you reduce the amount of friction by creating some kind of levitation, like they have in magnetic levitation of bullet trains. So there is hardly any contact between the body and the surface, so there's hardly any friction. Okay, so that kind of situation. So in that, if we have a certain body, okay, which is moving with a certain velocity v, So what will happen over here, because this is a frictionless surface, the body moves with uniform speed or velocity. Why? Because the net force on the body is 0. Okay. So in this case, when we visualize what is happening for the distance traveled by the body with respect to time. So let's say this is where the body was at t equal to 0. After some time t, it's reached here. But during that motion, the speed is constant. So you can see that the distance as a function of time is becoming speed into time. So if we now visualize the graph of distance versus time, or we want to understand how distance is varying with time, what kind of a graph we'll get? We'll get a straight line graph with a uniform slope. Because if we mathematically plot this relation, that the distance traveled at some time t is equal to a uniform value of v into t. So we'll see that we get a straight line graph like that. S is equal to vt. So basically this is a straight line graph of the type y equal to mx plus c. Okay, where m is the slope, which is constant. Okay, c is the y-intercept, which is also constant. Okay. And as you know, this point where it intercepts is 0, c. And if you look at the line, how it intersects with the x-axis, then m is equal to tan theta, which is also equal to y2 minus y1 upon x2 minus x1 with respect to any 2 points on the straight line. So I'm just reiterating the properties of the straight line, the meaning of slope, the meaning of rate of change, and all these things. Okay. So in this graph now, okay, what can we say about, suppose this time is some t1 and this time is some t2. Okay, what about average speed from t1 to t2? What can we say about that?
The distance traveled in that time interval by t2 minus t1.
Okay, yeah, so that's true. So for example, in this particular case, if this speed was, let's say, 10 meters per second, okay, so then what can I say about the average speed from t1 to t2? Should I say that, okay, I can't calculate till I know the value of t1 and t2, or should I say that it's actually calculable here? How much will be the average speed between, okay, now suppose I take an example where t1 is, let's say, 1 second and t2 is, let's say, 3 seconds. Now can you tell me how much it should be over here? Anybody has the answer?
It should be 10.
Should be 10 only, no?
Yes.
Because see, what will happen here is that it doesn't matter how much this t1 and t2 is, and therefore how much s2 and s1 is, because it's a straight line, no? It'll all be the same. This delta s by this delta t will be the same for all intervals of time. Okay, so the average speed, which is s2 minus s1 upon t2 minus t1, is equal to constant only. It's equal to 10 meters per second. But why is this happening? This is because v is uniform, because it is moving at a uniform speed. So the average speed is equal to that uniform speed for any interval of time. This is for any interval. Is this point clear to all of you? So even if I make, therefore, instantaneous speed, which is delta s by delta t, for delta t being very small, that will also be equal to the uniform speed only. No? which will be 10 meters per second. So what we are understanding here now is that whenever we have motion with uniform, what is basically called uniform motion, right? Uniform motion is motion with uniform speed or with constant speed. We have average velocity or average speed for any interval of time is equal to instantaneous speed at any instant, which is equal to the slope of the S versus T graph. Okay, so average speed for any interval during the motion is equal to instantaneous speed at any instant during the motion is equal to the slope of the graph. Okay, so now we are going to compare this with another situation, but this is the, this was the understanding of speed versus distance or distance time graph giving us speed till we came to the situation where we are talking about the falling apple and we are talking about accelerated motion. Up till that point, we are talking about the motion according to Newton's first law, where if the net force acting on a body is zero, it should move in uniform motion. So its distance versus time should look like a straight line graph like this. So it doesn't matter whether we are calculating the slope between, we are calculating the slope between this point and this point, or we are calculating the slope between this point and this point, or we are calculating the slope between 2 points which are very, very close to each other, like this point and this point. Now, it's always going to be the same. It's going to be tan theta. Okay. So the average between A and B will be equal to the average between C and D. Will be the average between any 2 points will be equal to the average at any particular point E, let's say. Okay. So the average from A to B will be equal to the average from C to D will be equal to the instantaneous at E, which will be equal to nothing but tan theta, which is the slope of the straight line. So that is the interesting and important property about uniform motion. So when we talk about uniform motion, there's no difference between instantaneous speed and average speed. They're all the same thing because the speed is never changing itself. It's a very logical thing, but this is how we interpret that geometrically. Okay. So just make a quick run through of this. Then we will talk about the situation of accelerated motion and see how it changes drastically in that case. Okay, so also additionally, what we can see is that if we are taking the value of V as 10 meters per second in this, then when we talk about a visual representation of the straight line motion with constant speed instead of the graphical representation, you can see that if it started from here at t equal to 0 with a uniform speed of 10 meters per second, then after 1 second, it will be at s equal to 10 meters. Okay. After 2 seconds, it will be at 20 meters. Okay. So in equal intervals of time, it's covering equal distances. But that also means that if we take a very short interval of time, some t equal to t plus delta t. That very small displacement delta s, or that very small distance covered, will become 10 delta t. So we can see that delta s by delta t for small delta t is equal to 10 meters per second, whereas in equal intervals of 1 second also it's covering 10 meters. So that's how this graph translates when we take the value of v as 10 meters per second. Now let's compare this situation to the observed situation when there is acceleration involved. So for that, let's take the example of a body in free fall, like the apple that Newton saw falling. Okay, so in that case, what is happening? The net force acting on the body is equal to its weight. So it's not zero. Okay, so the net force is not zero. Okay, so what is happening? It is having a variable speed as it is falling. Okay, so let's say the object starts from here at t equal to 0, from a certain height above the ground level, and gravity is acting like this on it. So what will happen is that after 1 second, maybe it's over here, but after 2 seconds, it will be here. Okay, after 3 seconds, it might be here. So you can see that in equal intervals of time, it is covering unequal distances. Why? Because the motion is accelerated. It has an accelerated motion. And also we can see that whatever speed it has here, it will have a larger amount of speed here. It will have an even larger amount of speed by the time it's 3 seconds. So V3 is greater than V2 is greater than V1, like this. So when we translate this, now I'm not going to use the equations as yet. You know how to use the equations, s is equal to half at square and all that. But I'm just saying, like, let's try to think that when this was first thought of experimentally, way back in the mid 1600s. So what people would have observed, that the relationship between distance and time should not be a straight line graph anymore, because in equal intervals of time, it's covering unequal distances. The distances are increasing. So that rate between distance and time, that relationship between distance and time should become something like this. So you can see that the amount of distance it is covering in 1 second, the first second, is different from what it is covering from 1 to 2, or is different than what it is covering from 2 to 3. Now in such a case, how will we calculate what is average velocity and what is instantaneous velocity? What is the difference between them?
Average speed, we can take a certain time interval and for instantaneous speed, we can take a very short time interval, and this can be done by constructing a tangent to that.
Yes, very good, very good.
At a particular
Okay.
point.
What about average speed? It will come by constructing what? Is there any construction we can do for average speed?
A tangent and finding the slope of the
Then
tangent.
instantaneous speed के लिए क्या होगा? अगर average speed के लिए tangent है, then what about for instantaneous speed?
We'll take a very short interval for that.
हाँ. So see, there are two types of lines. One is called a tangent, which basically just cuts the graph or cuts the curve at a particular point. Okay. Whereas the other type of line which cuts it at 2 points is not called a tangent. No? For example, if we are talking about a circular curve, it is called a chord. Are you following my point, beta?
Yes.
Yeah, secant line. Very good, Bhavika. That is the word I was looking for. Now, you might not have heard the term secant before. Okay. So I'll come to that. But before that, just what I was trying to relate with respect to circles. Okay. Now, all this aside, I'm just giving a general concept in geometry For example, if we have a circle, so let's say we've constructed a circle, and from some other point outside the circle, like this, let's say I draw a line from this point outside, which is just about touching the circle at one point. Then such a line is called a tangent. Okay, and it also, in the case of the circle, it has the property that it makes an angle of 90 degrees with the radius. So this is the center of the circle, this angle is 90. But basically what is happening, the tangent is a line that is just touching the circle at the point E. Okay, it is a straight line that barely touches the circle at the point E. Okay. But on the other hand, if I consider a line like this now, so I'm constructing this line from the same external point, this one, but it's going like this now. Now this line is very different because what's happening is that it is, let's say these 2 points are D and E. Okay. So the line, this kind of line is called, in the case of a circle, it is called chord. But the general term for it is that it is a secant line. Okay. So the secant line, PD, this one is a line, it's a straight line that intersects at two distinct points. There are two separate points, B and or whatever, D and E. So for example, if I was talking about a well-known geometrical figure, which is the circle, this is the difference between what we call a tangent line and a secant line. Okay. So I'll come back to rate of change, don't worry about that. I'll come back to instantaneous velocity and average velocity. But just talking in terms of coordinate geometry, okay, this is what we mean as the difference between a tangent and a chord in the case of a circle, or a tangent and a secant line. Okay. So you can make a quick understanding or jot down some note about this. Now the concept of tangent and chord is, or tangent and secant line, is not restricted only to a circle. It applies to any shape actually, in much the same way.
Sir, so supposing if we take a tangent in a square,
Yeah.
can we say that it can overlap with one of the sides, or does it have to
Yes,
go from
exactly.
the vertex?
100% correct. That's correct. Okay. Whether it is a square or you're just drawing a straight line also. So the tangent at any point on the straight line is nothing but the straight line itself. Okay. So for example, if we are drawing any polygon, it can have any number of sides. It may be a regular polygon, it may not be a regular polygon also. Now, if I want to draw the tangent at this point, it's nothing but this side extended. This is the tangent at the point A. Okay. But if I want to draw the secant line between the points, let's say B and C, then that will be this line. Okay. Now imagine a polygon which has infinite number of sides. That becomes nothing but a circle. Like you can inscribe a circle with an n-sided polygon. Okay. You can inscribe a circle with an n-sided polygon. Now just make n tend to infinity. So what will happen? Each of the sides of this polygon will tend to become a dot.
So can you please repeat?
Yeah, come again, beta.
So can you please repeat and get it?
Like, see, if you, so for example, a square is nothing but a four-sided quadrilateral, I mean four-sided polygon which is inscribed inside a circle. Okay, like that a pentagon is 5-sided, like that a hexagon is 6-sided. Okay. So like that, what I'm saying now, just imagine any general n-sided polygon inside a circle, inscribed inside a circle, n-sided regular polygon. So like this, if there are n sides, then how much theta will be? N-sided regular polygon.
E60 by N.
Yes, correct. Inscribed in a circle. So each of the sides will be subtending the same angle theta up to n sides like this. Okay. So theta will be equal to 2 pi by n, or 360 degrees divided by n. Okay. Now what happens if n is tending to infinity? If n tends to infinity, then each side becomes almost a point. Because the more the number of sides, the smaller the angle theta is. So in the case of n tending to infinity, theta will become like this now. Theta will become very small. Theta will be 360 by n, but n tending to infinity. So imagine a very large number of n, like 10,000 or 10 million or something. So then this becomes a point now. So that's another interesting way to talk about tangent. Okay. So if I was drawing the tangent at this point on the polygon, it would be this line only. Okay. But if I now select a polygon which has infinite number of sides, then it becomes a tangent, the circle itself. Okay, so this is a bit of an abstract geometrical idea, and we'll come back to ideas like this as we do more of calculus also. But is this clear so far? This thing, the n-sided polygon thing. Then each side of the polygon will tend to become a point.
Yes, sir.
Okay, so then if we extend that side of the polygon, that becomes nothing but a tangent. So anyway, coming back to the concept of tangent and secant. Okay, this concept applies. The concept of tangent and secant doesn't apply only to the circle. It applies to any general figure also. Okay. So I'll just show that elsewhere. Yeah. So the coordinate geometry concept of tangent versus secant line. Now let's take a different type of graph. Let's take the graph of a, like for example, let's take something which is very common in physics, as we are going to do. Let's take a graph like y is equal to x square. This is an example of a parabola. So that will look something like this. -1 and 1, its value is 1. At 2 and -2, its value is 4. At 3 and -3, its value should be 9, like this. Okay. Now for a parabola also, if we have two distinct points, like let's say A and B, and we join them by a straight line, then such a line is called the secant line. It is just a line joining any two points, any two distinct points. Such a line will be called a secant line. So this is an example of what we call a secant line. It's a straight line joining two distinct points. In this case, the points are A and B, okay, on a curve. In this case, that curve is the parabola. Y is equal to x square. Okay, that one. So this is how we define the concept of secant line, or define the secant line idea for any geometrical shape. It need not be just a circle or any curve. Okay, so hope the concept of secant line is clear over here. Okay. Now we will come back to the distinction between secant line and tangent line in just a moment. Okay. Now let's come back to our concept of distance versus time graph for an object in free fall. The original thing that we were discussing. We have an object in free fall, and we are looking at its distance versus time graph. Okay. For a body in free fall. Now here, if I ask you, what is the average velocity for a time interval t1 to t2 from t equal to t1 to t2? So we would say that the average velocity is displacement during that time, or the average speed rather. Okay, let's say this is, we're still talking in scalar terms, so this is average speed. Okay. So it would be S2 minus S1 upon T2 minus T1. So now if we want to interpret this quantity, geometrically in the diagram. So what we'd have to do is, suppose this time is T1. Okay. So this corresponding value of distance from the initial position is S1. Okay. And suppose this time here is T2. So I've given you T1 and T2, so you know how to plot them on the x-axis, which is the time axis. So the corresponding point on the graph at T2 is this point. Okay, so now you can see that in this graph, this over here, this value is my S2 minus S1. That is the distance covered in this interval of time, which is T2 minus T1. Okay. So if we just extend this over here, wait a minute, just magnify this to make it easier to understand. So this is the interval of time that I'm talking about. This is T2 minus T1. Okay. So coming back to the graph, if I join these 2 points with a straight line, what kind of a straight line that is called now? That is called a secant line. This line is nothing but the secant line drawn between the 2 instants of time T1 and T2. So what is this quantity over here? S2 minus S1 upon T2 minus T1. In context of this straight line, you can see that this is your delta S and this is your delta T. So you see in this triangle here, this is nothing but tan theta. For which line? It is for the secant line. So this becomes the geometrical interpretation of what we call the average velocity or the average speed. So the average speed, this is the slope of the secant line. Okay, drawn between the points which are at t equal to t1 and t equal to t2. That is the average speed. Okay, so delta S by delta T is equal to tan theta for the secant line. Tan theta is the slope. Okay, so this becomes the geometrical meaning or the graphical, you can say, representation of what is average speed in the case of this type of graph. The distance versus time graph for a free falling object. The distance will be increasing with time in such a way that the graph is curving like this. So between any two times T1 and T2, if I want to calculate the average speed, what I'll have to do is I'll have to draw a secant line joining those 2 points and then calculate the slope of that secant line. So that slope will give me what is the average speed. Okay, so just make a note of this point and understand this thoroughly. Then we'll discuss next about instantaneous speed. Okay, so now what you can also see that in this case, the average speed is not going to be same for all intervals now. So if you do a comparison of the earlier graph that we had, which was the case of uniform motion on a horizontal surface, we do a comparison of that one with respect to the comparison or with respect to this one now, which is free fall. So we are doing a comparison of S versus T for free fall and S versus T for uniform motion. Okay. So there the example was a body moving on a smooth surface. Okay. So it's unaccelerated motion. Whereas this is accelerated motion. Okay. So this was distance versus time there, but now something like this is distance versus time here. So here we can see that whether we take this time interval or we take any other time interval, it's all the same. V average from T1 to T2 is equal to V average from T2 to T3, which is equal to the uniform V, because our S was equal to Vt. Okay. But here, if we consider different intervals of time, you can see that the secant lines are changing. Okay, so this V is the slope of the line itself. So which line is the graph of V versus T? Okay, but in this case, we'll have to draw distinct secant lines. So you can see that V average from T1 to T2 is not equal to V average from T2 to T3. Okay, because they're different secant lines. So now if we draw these different secant lines, we can see here, for this one, it is this kind of line. For the second one, it becomes this type of line. So this is line 2, okay, and this one is line 1. So you can see that they are different secant lines. This is slope of line 1. So straight away we can see that aspect that we were talking about earlier, that in the case of an accelerated motion, the average speed itself changes from interval to interval. Whereas in the case of uniform speed, the average speed remains same, whatever interval we take, and that is equal to the uniform speed itself with which it's traveling, the uniform instantaneous speed. So now in this situation, how will we geometrically construct to calculate the instantaneous speed? Okay, that becomes the next question for us. So instantaneous speed. We know its definition. It is delta S by delta T, but with the condition that delta T should be very small. It should be extremely small. So we can even add another very. Okay, because it is speed at an instant. So now we want to understand that what kind of geometrical construction will give us the meaning of that. Or you can say geometrical interpretation. So again, let's say we are talking about that case of the object in free fall. So we will see that we'll come to that very interesting concept of slope of tangent. Okay. So we'll have to understand what we mean by tangent itself first. So distance versus time in free fall. Suppose this is this. Now this is some particular instant of time, suppose t0. Okay. So I want to calculate, we want to find the instantaneous speed at that instant. Okay. At the instant of time t equal to t0. So how do we do that? Okay. So we're going to have to apply this definition now. So this definition will have to be applied here. So geometrically, how we'll apply that definition, let's see. So first of all, we'll have to magnify this a lot. Okay. So I'm just looking at this magnified diagram of this now. Oops. Yeah. So at this particular instant, let's say the distance from the starting point was S0. Okay. Now, if I want a very accurate measurement of the, the instantaneous speed, what I'll have to do is I'll have to select another time, which is very, very close to this time. And even in this, I'm showing that there is some gap, but we have to imagine that this is much closer than what I'm showing. So this delta t is an extremely small interval of time. Like the example we had taken, it's 5 milliseconds or 10 milliseconds. So this value of time here will be t0 plus the delta t, where delta t is very small. So that means the distance has increased from whatever value S0 I had here to a value slightly greater than that. So it has become like this. So this distance, sorry, delta S, we'll come to the language of ds bit later. Okay, so delta S is the very small distance in delta t that it covers in time delta t. Okay. So by definition now, what is my instantaneous speed? My instantaneous speed is that delta S by delta t only. So now I'm trying to, understand what is the relationship between these 2 points in context of this definition here. So further, if I were to magnify this diagram by a huge amount, okay, if I were to put this under my magnifier and understand how this looks, I realize that the curve, I'm magnifying it several times, so the curve is like this at that point. Okay. Now on that curve, on the curve, the point T0 is somewhere here, and the point T naught plus delta T is over here. So this is my delta T. And this is my delta S. Okay. So now if I were to join these 2 points with a straight line and extend that straight line, that would be something like this. So this line is precisely what I would call the tangent line at that point. So coming back to this diagram, I would have to construct a line like this now, which is nothing but my tangent line. So as you can see, it's not even easy to construct, let alone calculate. So this kind of a line would be my tangent line. So I would have to join these 2 points which I have drawn over here. The point at t equal to t naught and the point at t naught plus delta t. I'd have to join those 2 points with a line which is then called the tangent line. So in the situation where I'm doing this calculation very precisely, my delta t is extremely small. The smaller the value of delta t, the more accurate it is. Okay. So now the point here is, in this construction, if the tangent is drawn perfectly, okay, then basically the points at t equal to t naught and t equal to t naught plus delta t, these 2 points over here should almost merge, or at least they should be consecutive points. They should be consecutive to each other. So that basically means that delta t should be tending to 0, so that those 2 points almost merge with each other. Okay. And in that case, I can see that my instantaneous velocity at the time t naught is nothing but slope of the tangent. It is equal to tan theta. So from that, I can see that the instantaneous speed, but now I have a condition that in that not only delta t is very small, it's so small that it's almost equal to 0. It's tending to 0. That is equal to the slope of the tangent. Okay. The S versus T graph. So that is the difference between instantaneous velocity and instantaneous speed and average speed in terms of the graphical representation or in terms of the geometrical representation. Average speed becomes slope of secant line. So line joining 2 distinct points which are drawn at t equal to t1 and t2, because we are calculating the average speed from t1 to t2. Okay. But instantaneous speed, that becomes what? That becomes slope of tangent line. So that is the line tangent to this to S versus T graph at the point T equal to T naught. Okay, so this is instantaneous speed at the instant T equal to T naught. So that is the difference between these two things. Okay. So this is the geometrical representation of instantaneous speed. Geometrical or graphical. Interpretation of instantaneous speed. Okay, so just take a moment to go through this. We will discuss more about this in the next few minutes. If there's any doubt at all, please let me know. I will discuss again. Okay, people, any doubts? Yeah, Rohan, I will be sending the recording of the lecture as well as the the whiteboard notes in PDF, okay, after the lecture. Only it will take a few hours for me to send it because the lecture recording first has to upload on our channel. Then I'll send you the link of that, okay, on the group itself, okay. So in case you have missed any part of the lecture because of connectivity issues or in between, maybe audio was not clear because of connectivity, etc. Don't worry, you will have access to the full recording of it by today evening. Okay. Right. So now let's look. Yeah, Beta, tell me.
Yes, sir. You had written on the right side under instantaneous speed that S versus T graph at point T naught is there. It's not there. What does that mean?
Ria, just a second. I have written which one? Yeah, come again. This part?
Sir, on the right, I think.
On the right?
Yes, sir.
Okay, this part?
Yes, sir. The
okay,
last
just a second. Let me minimize this a little. Yeah. So instantaneous speed at the time T naught is equal to the slope of the tangent line, which is the line tangent to S versus T graph at the point T equal to T naught.
Oh, okay, sir.
So, and that is what we are constructing over here. As you can see, this is the construction of the tangent line at the point T equal to T naught. So basically what we have to do is like, it's very imaginary. Like, every curve, you can visualize any curve as a series of dots, one after the other. So at a particular time, there is a particular dot. So we have to take that one and the next consecutive one and join them into a straight line. So that's, sort of very intuitive way of trying to say what a tangent line is. Right. Or another way to understand it would be like, since we live in the digital era, okay, just try to visualize what I'm saying carefully. If I have any digital image, right, any sort of picture which has lots of colors and things like that, so I see them as continuous lines of color, continuous curves of color. But what happens if I magnify this a lot? If I magnify it a lot, it will pixelate. So when it pixelates, what happens? Instead of seeing continuous colors, I will see pixels of colors. Right? Instead of seeing a continuous blob of color like this in the diagram, I will see pixels of color like this, and their outline will be like that curve. Understanding the point of what I'm saying, people? Okay. So like that, in any two-dimensional graph, if I have any two-dimensional graph, so y is some kind of function or relation of x in that. Okay. Now, if I magnify a part of that graph enough, then what will happen is that it will not be a curve like this. That magnified version will, just like an image pixelates into pixels or boxes of color, this will pixelate into something like this. So what was looking like the curve in the outline like this, when I magnified this portion enough, it would become a series of small little line segments. So at a particular instant of time, whatever time T naught I have, that time T naught corresponds to one particular small line segment like this. So all I have to do now is extend that line segment and I get my tangent line. So that is the tangent at that point. That is the construction of the tangent. So this is all okay as far as imagination is concerned, but it does not actually give us any formula or any method of calculating the slope of the tangent. So the job of differential calculus is to give us a set of systematic methods, formula, etc., how to calculate slope of the tangent. We will see that later, of course. So in the next lecture, I haven't finished yet, okay, but in the next lecture, we'll learn how we use the method of differential calculus. Okay, differential calculus is used to find the slope of tangent for any sort of equation, for any sort of curve. Okay. So I'll just take a couple of minutes before we finish. I know you must be hungry and tired. It's 1 o'clock, but okay. But yeah, you did have only one lecture today, so you can bear with me for a few more minutes. Okay. So now let's take a numerical example. So suppose we have a situation where a particle moves along a straight line such that it is given to us that its distance varies with time according to this relation. Okay, where s is distance in meters, okay, and t is time in seconds. So first of all, we want to plot an approximate graph of s versus t. This should not be too difficult, right? Then we want to find the average speed from t equal to 0 to 2 seconds, and then again from 2 to 4 seconds. So this should also not be difficult because we have a formula for it, right? But the third part is going to be the slightly more tricky part, where we'll find the instantaneous speed at t equal to 2 seconds. Precisely at t equal to 2 seconds, we want to know what the instantaneous speed is. Okay. So I'll just give you a couple of minutes to start off with the graph and try and understand how you can interpret these things from the graph also. Okay, and then we will see about how we can use the definition of instantaneous speed to calculate the value of the third part. Okay, so let's look at let's get a rough idea about the graph. Oops. Right, so this will be a bit like the free falling object. You can get a good idea about how distance is changing with time by just looking at some values. S is equal to t square. So for example, t equal to 0, s is equal to 0. T equal to 0.5 seconds, s will be 0.25 meters. T equal to 1 second, s will be 1 meter. 1.5 seconds, sorry, 2.25 meters, okay, 2 seconds, 4 meters, 2.5 seconds, 6.25, 3, 9, okay, 4, 16, so and so forth, so and so forth. So you can see that there's a rapid change in the slope, the curve. Eventually it goes very sharply up, because you can see the sequence in which how the distances are changing. So it's something like this, okay. Well, let's say this was 1 second, this was 2 seconds, this was 3 seconds, and this was 4 seconds. Then so this is roughly speaking what the graph is like, right? So now this part we want to calculate average speed from 0 to 2 seconds. It was first. So that is, we have to make a secant line. Okay. We can calculate it by formula also, but I want to do the geometrical representation here. So for this, I will have to join these 2 points. Time t equal to 0, from there up to t equal to 2 seconds at this point, and calculate this slope. This is secant line joining t equal to 0 to t equal to 2 seconds. So this V average will be slope of secant line. So that will be this tan theta. Okay. So that will be, as you can see, 4 minus 0 upon 2 minus 0, or 2 meters per second. That should be the answer for the first part. I mean, A part of this is 0 to 2 seconds. Now, likewise, for the second part, I mean B part of second part, I want to calculate V average from 2 to 4 seconds. So now I'll have to make a new secant line joining these instants of time. So I'll have to join this point here and this point here with a new secant line. I have to calculate the slope for this one. Oops. That. So this is my secant line from 2 to 4 seconds. Okay. So I'll have to calculate this tan theta. So this you can see is 16 minus 4, or a distance of 12 meters in a time interval of 2 seconds. So 6 meters per second. So if you compare the two secant lines, you can see how different their slope is also. So what you are seeing geometrically, the evidence that you're getting visually from the graph, that same is showing up in your calculation also. But in calculation, it's showing up precisely. That it's not just that it's more, but it's actually 3 times. This one slope is 3 times this one slope. This one slope is 6 meters per second, whereas the first one slope was 2 meters per second. Okay, so now we come to the more complicated business.
Yes.
Okay, so if anybody has a doubt in this part, please let me know, whether it is the calculation part or the diagram or whatever. Just don't hesitate, let me know. Okay, now let's go step by step and let's see about the instantaneous speed, the third part, at t equal to 2 seconds. Instantaneous speed p at t equal to 2 seconds. So first of all, what we are trying to do here is that at this point of time, t equal to 2 seconds, we'll be trying to draw a tangent line. That is, let's say this line. Just drawing a rough line over here. Okay. So this is the tangent line at t equal to 2 seconds. So we want to find the slope of the tangent. Okay, that one. Okay. But algebraically, what I should try to do, I should calculate delta s by delta t for a very small value of delta t. Should be extremely small. Okay. Now, can any of you suggest a suitably small value of delta t? Yeah, somebody please suggest some suitably small value of
1
delta t.
millisecond.
1 millisecond. Okay, very nice. Let's take. Okay, so let's take delta t as 1 millisecond. So that is 0.001 seconds. Okay. So when I magnify this graph now, what I'm trying to do is that so let's say this is the value of time that I have, which is t naught equal to 2 seconds. Now this next value of time that I have to take, like the next consecutive point almost, that will be how much? That will be t equal to 2.001 second, according to the value of delta t that I have taken. That's correct. Okay. So whatever this value of s naught, now this next value will be s naught plus delta s, because this will be my delta s. This was my delta t, and I have taken delta t to be 0.001 seconds or 1 millisecond. Okay. So this will be s naught plus delta s. Okay. So if I'm doing this, so I'm taking t naught as 2 seconds. So my s naught is how much? It is 2 square or 4. Or I'll just write it as 4, but we should understand that it's up to a precision, because 2 is also precise. So it is 4 meters. Okay. But my next thing, which is t naught plus delta t, according to this value, is 2.001 seconds. So what should be my value of s? It should become s naught plus delta s, and that should become how much? 2.001 square. So can somebody do me the favor of doing this calculation and telling me how much it is? This will come out to be how much? Yes, very good. That's correct. It will come out to be 4.004001 meters. Okay. So now based on this value of delta t, that is, the accuracy depends on how small I've taken. So I've taken it quite small. So my instantaneous speed, which should be delta s by delta t, when I'm taking that delta t to be 1 millisecond, it's coming out to be 4.004001 minus 4.000, like this I can write it, divided by the time interval, which is in meters. So you can see it is 4.001 divided by 0.001. oh sorry, it's 0.004 divided by, so then it will become 4. So it is 0.004001 divided by 0.001. So that is 4.001 meters per second. So that's nearly equal to 4 meters per second. Okay. Now I'm running out of time a little bit, so I'll just give you something to do yourself as a homework later. Check in this same thing, if delta t is taken as 1 microsecond, that is 10 raised by minus 6 seconds, that is 0.000001. Okay, then see what is the value of v you will get. Okay, and when you do this calculation in the same manner, you can use a calculator, you can just do by some manual calculation, whatever, you will see that it will come even more precise. It will come as 4.000001 meters per second. So in fact, now what we can do is, if we take a general value of delta t, now next we take, if delta t is so small that it is tending to 0, then we'll see then p, which is delta s by delta t, will become 2 plus delta t whole square minus 2 square divided by delta t, but with the condition that delta t is extremely small, so it's tending to 0. Okay, so when you open this bracket, you'll get 4 delta t plus delta t square divided by delta t. Okay. So this will further become 4 plus delta t, but under the condition that delta t is so small that it's tending to 0. So you can see it will become 4. So the exact value of instantaneous speed is actually 4 meters per second. But because we were taking because we were taking 1 millisecond, we were getting a bit of error. We were getting it as 4.001. If instead of taking 1 millisecond, we took 1 microsecond, then the error is even lesser. The error is in the 6th place of decimal. Here it was in the 3rd place of decimal. But like that, if we take delta t to be so small that we assume it is almost 0. So tends to 0 means that it is so small that it is almost 0. Okay, but not exactly equal to 0. It's still a time interval, but it's almost equal to 0. Then we will get the precise value to be 4 meters per second. So what this is showing us, that if we were to draw perfect tangent such that the distance between these 2 points was tending to 0, so they're almost merging into 1 point, then the exact slope of the tangent we will get will be exactly equal to 4 meters per second. Okay. So this is the story of slope of tangent, and the instantaneous speed as the instantaneous rate of distance with respect to time in terms of the idea of that slope of tangent. Okay, so this is the starting point of basic calculus. This is the problem on which Newton was thinking along when he invented differential calculus way back in the 1600s. Okay, so this is where we'll stop today's lecture, and the next lecture that we have on calculus, we will look at more some more definitions, some more precise terms, and then we'll start looking at how to develop the formulae of differential calculus to be able to calculate the rate of change without so much of effort like we've done over here. We put the value of delta t as very small, then we have approximated it, this, that. So all this will not be required once we understand the formulae and method of differential calculus. Okay, so hope today's session was clear to all of you and hope you enjoyed it. Okay.
Yes, sir. Thank you, sir.
Okay, people. So yeah, that's it for today's session. Wish you all the best. I will be sending you the recording and the notes by today evening, and you revise that in the next couple of days. I'll also send you a worksheet of few problems which will help you revise these concepts in the next few days, so that by the time we meet for the next lecture, you will be well prepared for what's coming up in calculus. Okay? That's it for today's session, people. All the best.
Thank you, sir.
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 Thank you, sir.